Hello, you're in a class with OPiyo for chemistry, and in this session we are going to be calculating pH of strong acid and strong bases after neutralization reactions. In the previous session we covered the pH of strong acids as well as pH of strong bases. This time round we need to find out the pH after the reaction, which means we are going to be calculating actually the resultant pH of a solution after an acid-base neutralization reaction. And if you have not yet subscribed, please kindly subscribe for more of this kind of sessions. During any titration reaction, the hydrogen ion from the acid will react with the hydroxyl ion from the base, forming water molecule. That process is known as the neutralization reaction. And in all cases, the hydrogen ions will be reducing from the acid, as well as the hydroxyl ion will also be reducing from the base. When the number of moles of the two are the same, then the pH is going to be neutral, and if it is at room temperature, the resultant pH is going to be equivalent to a value of 7. Then if in any case the strong acid is more than the strong base, the resultant pH is going to be less than 7, because the resultant solution is acidic due to the excess of hydrogen ions from the strong acid. And when the strong base is more than the acid, the resultant pH is going to be greater than 7, because the solution is containing excess of hydroxyl ions from a strong base. Our case 1 is when the strong acid is in excess. In this question, we have 25 cubic centimeters of 0.02 molar sodium hydroxide solution reacted with 30 cubic centimeters of 0.025 molar sulfuric acid, and we are required to calculate the pH of the resultant solution, or the pH at the end of the reaction. So in our solutions, we are going to work out the number of moles of sodium hydroxide available for the reaction, as well the number of moles of sulfuric acid available for the reaction before we can do any other thing. And for us to do that, we are going to use the first principle approach, that is 1000 cubic centimeters of sodium hydroxide solution contains 0.02 moles. Then 25 cubic centimeters of sodium hydroxide solution will contain 25 times 0.02 divided by 1000. This will give us a value of 5 exponent negative 4 moles. And the same way for sulfuric acid, we would say 1000 cubic centimeters of solution of sulfuric acid contains 0.025 moles. What about 30 cubic centimeters of sulfuric acid? That would contain 30 times 0.025 divided by 1000. That would give us 7.5 exponent negative 4 moles of sulfuric acid. So initially we have 5 exponent negative 4 moles of the base and 7.5 exponent negative 4 moles of the acid. So our next step there is going to be to establish the equation of reaction. That is 2 moles of sodium hydroxide is reacting with 1 mole of sulfuric acid to produce 1 mole of sodium sulfate, and the 2 moles of water. In the equation is not shown, but there are 2 moles of water there. Now in this case we can extract that statement and use it to calculate the number of moles of sulfuric acid that will have remained, because from this we can notice that sodium hydroxide is less than sulfuric acid, which means the acid will remain at the end. So we treat what will determine what to be on the left is the amount. The sodium hydroxide is less than the acid, therefore we're going to keep it on the left hand side, and then the unknown, that is the amount of reacted sulfuric acid, will be on the right hand side because we are looking for it. So we say 2 moles of sodium hydroxide react with 1 mole of sulfuric acid. This implies 5 exponent negative 4 moles of sodium hydroxide will react with a half of its value of sulfuric acid, so that would be 2.5 exponent negative 4. So in this case we know the number of moles of sulfuric acid that will have reacted. Then we now need to go ahead and find how much of the sulfuric acid will have remained. We had 7.5 and now we have got that the reactant one is actually 2.5. So we subtract the two to get the value of unreacted sulfuric acid or the excess sulfuric acid. So the original one is 7.5 exponent negative 4, the reacted is 2.5 exponent negative 4. So that gives us the number of moles of excess sulfuric acid as 5 exponent negative 4 moles. And now that we have the number of moles of excess sulfuric acid, what we need to know now is that this number of moles are contained in a new volume, not in the original volume. So it is necessary for us to calculate the new volume. That is, we get the volume of the acid, we added the volume of the base, and we get the total volume of the resultant solution. So that would be 25 plus 30, giving us 55 cubic centimeters. Now after knowing this, we can use this to calculate the molar concentration of excess sulfuric acid by transferring it from 55 to 1000. So that we would say 55 cubic centimeters of solution contains 5 exponent negative 4 moles of sulfuric acid. What about 1000? That would be 1000 times 5 exponent negative 4 divided by 55, giving us a value of 0.0091 molar as the concentration of the excess sulfuric acid. And after obtaining the concentration of excess sulfuric acid, then we have actually gone back to the calculation of the pH of a strong acid. That is one, by writing the equation of reaction, that is the dissociation of sulfuric acid. And from that equation, we are going to be able to obtain the molar concentration of hydrogen ions, because 1 mole of sulfuric acid produces 2 moles of hydrogen ions, which means the molar concentration of hydrogen ions will be twice the molar concentration of sulfuric acid. So obtaining that from our equation, we can substitute the molar concentration of hydrogen ions in the pH expression, and this should be able to give us a pH of around 1.74 as the pH of the resultant solution. Try out the following numbers, and where you get stuck, you will forward your concern on the WhatsApp number that will be given at the end of this video. So let's tune in and look at the situation where we have the acid and the bases reacting, but we have the base in excess. We have a task here. Calculate the pH of a solution made by mixing 75 cubic centimeters of 0.02 molar sodium hydroxide with 25 cubic centimeters of 0.025 molar sulfuric acid. You can ignore the English too. So in our solution, we're going to do it in the same fashion like in the first number. So what I want you to do here, you can pause this video and find the original number of moles of these reactants, number of moles of sodium hydroxide and number of moles of sulfuric acid. Okay, we have 1000 cubic centimeters of solution contains 0.02 moles of sodium hydroxide. And what about 75? That would be 75 cubic centimeters times 0.025 divided by 1000 cubic centimeters. That would give us 1.5 exponent negative 3 moles of sodium hydroxide available for reaction. Then on the other hand, for the acid, we have 1000 cubic centimeters contains 0.02 moles of sulfuric acid. What about 25 cubic centimeters? This will be 25 cubic centimeters times 0.02 moles divided by 1000 cubic centimeters, giving us 5 exponent negative 4 moles of sulfuric acid for the reaction. Having that done, our next step is to write the equation, and we use it to calculate the number of moles of the excess reagent. So sulfuric acid reacts with sodium hydroxide in a ratio of 1 to 2. So 2 moles of sodium hydroxide reacts with 1 mole of sulfuric acid. And since the sulfuric acid is limited, as you can see from the number of moles calculated, sulfuric acid is actually very small. So its amount will be finished or sulfuric acid will react completely, and the remaining reagent will be sodium hydroxide. So we're going to start with the acid in this case by saying 1 mole of sulfuric acid reacts with 2 moles of sodium hydroxide, which means 5 exponent negative 4 moles of sulfuric acid will react with twice its number of moles for sodium hydroxide solution. So using that, we obtain number of moles of reacted sodium hydroxide as 2 times 5 exponent negative 4, which is going to be 1 exponent negative 3. Now, this number of moles of sodium hydroxide reacted can still be used to obtain the value of the excess sodium hydroxide. That is, by getting the original number of moles of sodium hydroxide and subtracting the reacted one. So let's obtain that. Will be 1.5 exponent negative 3 minus 1 exponent negative 3, giving us 5.0 exponent negative 4 as number of moles of excess sodium hydroxide. And the excess sodium hydroxide is in the total volume, and the total volume there is going to be 75 plus 25, giving us 100 cubic centimeters. So using this total volume and the number of moles of excess sodium hydroxide, we can calculate the new molar concentration of the sodium hydroxide in excess. That is, we say now 100 cubic centimeters of solution contains 5 exponent negative 4 moles of sodium hydroxide. Then what about 1000 cubic centimeters of solution? Will be containing 5 exponent negative 4 times 1000 divided by 100, and that will give us 5 exponent negative 3 molar. So this has given us the molar concentration of sodium hydroxide, which we can use to obtain the molar concentration of the hydroxide ions. Since the mole ratio of the reaction between sodium hydroxide and hydroxide ion is 1:1, it means the molar concentration of hydroxide ion is going to be the same as the molar concentration of sodium hydroxide. And after obtaining that, at this point we now go back to calculation of pH of a solution of a strong base. Here you have 2 options from this point. The first option is to get the pH from the molar concentration of the hydroxyl ion. Then after getting the pH, you are going to subtract it off from 14, and then you get the pH of the resultant solution. And the second option is to use the Kw, the value of Kw, which is 1 exponent negative 14 moles squared decimeter power negative 6, to obtain the molar concentration of hydrogen ions. Then use the molar concentration of hydrogen ion to calculate the pH of the resultant solution. Whatever method you choose should take you to the same answer. So we are starting with pH, and our pH gives us a value of 2.30. Then for us now to obtain the pH, we are just going to subtract pH from 14. That will give us a value of 11.699, which is approximately 11.7. Then the other option is use Kw and concentration of hydroxyl ion to obtain the molar concentration of hydrogen ions. And if we get Kw divided by molar concentration of hydroxyl ion, it will be able to give us the molar concentration of hydrogen ions, which is 2 exponent negative 12 moles per decimeter cubed. And we have pH is given by negative logarithm of molar concentration of hydrogen ion, which is negative logarithm molar concentration 2.0 exponent negative 12, and this gives us a pH of 11.699, which is approximately 11.7. So whatever approach you use must always take you to the same value of pH. So that is all, and I want to leave you with the following numbers that you can be trying after watching this tutorial. And when you get stuck, please don't stay alone. In all cases, you will have your Kw as 1 exponent negative 14 mole squared decimeter power -6. And when things really get tough, don't hesitate to consult. You can always contact me via my WhatsApp number you see on the screen, or use my email address that you're seeing there. You can even put anything on the comment section. I will always be visiting it and checking it. I will be ready to reply to your queries. Thank you so much for your time and for following up this tutorial. If you have not yet subscribed to this channel, please kindly subscribe and hit the notification bell so that the next time I upload the video, you will be informed and you won't miss a single session of this branch of chemistry. My name is OPiyo George, and I'm very glad to have had this precious time with you. Thank you so much.